Hello there, Mr. Sutton bringing you a lesson on operations and compositions of functions. In this one, we'll figure out how to add, subtract, multiply, and divide functions. And we'll evaluate and simplify composite functions. As a real-life application, we're going to figure out how to apply discounts, multiple discounts at a store. As a warm-up, we'll do a little business problem here. Let's say that the profit after X months of two companies, we'll call them F and G, is given by the two functions below. So here's the profit for the F company, x squared minus 4, and here's the profit for the G company. We'll call that x minus 2. Now let's say these companies merge to form F plus G Incorporated, a very creative name there. What is the function for their combined profit? And what is the profit after 8 months? So the first question we could phrase by writing it like this. We could say F plus G of X. And the second question, what's their profit going to be after 8 months, we could write as follows. F plus G of 8. So this is kind of like function notation, only we're not dealing with just a single function anymore. So pause the video and take a sec to see if you can figure out what you need to do in each of these two cases. Okay, let's bring it together and see if you got it the right way. So for this situation, when you just have x here, all you need to do is take the original algebraic functions and add them together. Do whatever it says to do in here. So we've got the f function, x squared minus 4, plus the g function, x minus 2. So this is just saying f of x plus g of x right here. And we just have to simplify that. So we've got x squared minus 4 plus x minus 2. The minus 4 and minus 2 can combine for minus 6, but otherwise everything is just going to stay the way it is. Now over here, when we have this 8 getting plugged in, this is just saying whatever this combined function is, plug 8 into it. So you could take the function you just came up with over here and substitute 8 for x, calling this 8 squared plus 8 minus 6. So that's 64 plus 8 is 72. Minus 6 is 66. Now another way to do this is you could actually plug 8 individually into the two original functions. So we could write f of 8 plus g of 8, and then just plug 8 into each of those. Plugging 8 into the f function, that's 64 minus 4, which is 60. Plugging 8 into the g function, that's just 8 minus 2, which is 6. And 60 plus 6 is exactly what we got before, 66. We're going to try out some more operations on these functions now. So using the same kind of reasoning we used when we did f plus g of x, pause the video and see how many of these we can get. All right, let's see what you came up with. So for this one, we're doing f minus g, so we're doing basically x squared minus 4 minus quantity x minus 2. Basically, we just need to distribute that negative and combine like terms. So we've got minus x plus 2. So then that'll be x squared minus x minus 2 when the dust settles. Next, we have f times g. So that's just multiplying these two functions together. For this, we can just FOIL. So we've got x to the third, and then minus 2x squared minus 4x plus 8. For this last one, we've got f divided by g of x, so we have the f function over the g function, basically. This one, it turns out we can go a little bit further and simplify it. Whenever you have a fraction, you're supposed to try to reduce it as much as you can, which means if you have a common factor that you can cross off in both of them, you're supposed to do that. Well, how do we know if we have a common factor? Let's factor the numerator. X squared minus 4, what's that factor into? Oh, well, x plus 2 and x minus 2. We have an x minus 2 up here and down here. We can cross those out because that's common factor. You're basically dividing this by itself, so it's 1. And then that leaves us with x plus 2. We have to be a little bit careful, though. We can't just write x plus 2 and be done with it. You have to exclude x values that make the original function undefined, even if they don't make the simplified function undefined. So we actually have to write x plus 2 for x not equal to 2. This seems kind of picky, but if you think about it, this function is supposed to be equivalent to this function up here. It's supposed to have all the properties of this function up here. Well, one of the properties of the original function is that 2 makes it undefined. So in order to keep that property with this simpler version, we have to stick in this little caveat. The next several examples are going to deal with something entirely different than adding or multiplying functions together. For this one, we're given two functions. F of x is x squared plus 10 and g of x negative 4x minus 8. And we're doing f of g of negative 5. So this is a weird notation, and it gets weirder. They sometimes write it like this. If you want to use your parentheses form here, they'll sometimes write f with a big open dot and then a g with something else out here. These two things mean the same thing. This is called a composition of functions, or a composite function. This is a function that you get when you plug one function into another function. Now, the way these work is you have to start with the inner function and work your way out, evaluating as you go. So right here what's happening is negative 5 is being plugged into this inner function of g. We're going to get an answer from doing that, and that answer is going to get plugged into this outer function of f. And if you're using this open dot parentheses notation, you just go from the closest function to the number here, working your way left. So we have to do g of negative 5 first. That's going to be negative 4 times negative 5 minus 8. And evaluating that, that's going to be 20 minus 8, or 12. This number now, this is g of negative 5 right here. So when you say f of g of negative 5, you're really saying f of 12. So let's go ahead and plug that into the f function now. The f function squares and then adds 10. So this is 12 squared plus 10. That's 144 plus 10 for a total of 154. For our next example, we're not going to use any constants. We're going to do g of f of x, or g open dot f of x, and we're going to use the same functions as before. Now this situation is in some ways easier and in some ways more difficult. It's easier because you already know, for example, what f of x is. F of x is just x squared plus 10. They gave it to you. They literally said f of x equals this junk over here. So instead of writing g of f of x, you can immediately write g of whatever this stuff over here is, x squared plus 10. Now that's the easy part. The tricky part is that now you're not plugging a constant into this outer function anymore. Now you're plugging an expression with some x's and maybe more than one term in it. So that might be difficult to work with, more difficult than working with a constant. G of whatever you plug into it, remember the g function, you're multiplying by negative 4 and subtracting 8. So instead of writing g of this stuff, we can write negative 4 times x squared plus 10 and then minus 8. Wherever you see an x in the g function, you're just going to plug x squared plus 10. Let's simplify that now. This will be negative 4x squared minus 40 minus 8. And then subtracting these numbers out here, we've got minus 48. So you might be wondering where you could use composition of functions in real life. It gets used quite a lot in computer programming, but here's a less computery example. Let's say we have a hardware store with a sale going on, and they've got 3 different discounts. You have to use all 3, but you can choose the order that you use them in. So let's say that we have a Funkadelic discount, which we'll call f of x, where you take the square root of the price of an item. And let's say there is a Groovy discount, which we'll call g, where you multiply the price by 6 and then subtract 3. And then let's say we have a Happy discount, where you divide the price by 3. So x over 3. So let's say that you decide to go Funkadelic, Happy, and then Groovy. So we've got a function, an f function. We're plugging that into an h function, and then we're plugging that into a g function. So this is a composition of functions here. So they want to know how much a $9 hammer is going to cost after you apply that in this order. So we're plugging 9 into this. and they want to know a formula for the price of any item after this series of discounts. So g of h of f of x. So pause the video, take a sec to see if you can figure out these two items. The functions here aren't all that nasty, but there's 3 of them now. So again, start on the inside, work your way out, and we'll see what you come up with. All right, let's see what we came up with for the constant version of this problem. So we have 3 functions, g, h, and f. The f function is the most inner function, so we have to do that one first. So that's going to be square root of 9 that we have to do first, f of 9. That gives us 3. We then have to plug that into the next function out. That would be the h function, because whatever f returns, h gets to play with now. So h takes a number, divides by 3. So we're doing h of this number 3, and dividing that by the 3 that is in the h function itself, so don't mix up those 3's. That gives us 1. And then this 1 finally gets plugged into the g function, so that's going to be 6 times 1 minus 3, which gives us, ironically, 3. So that's the price of a hammer after all these discounts are applied. Let's go ahead now. Ooh, fancy. And move my cursor out of the way. There we go. Let's do x instead of 9 now, because it's kind of annoying if you have to keep plugging numbers into all 3 functions. Wouldn't it be nice if there was just one single function that does all of this stuff for you in one shot? So let's see if we can come up with that over here. So x just gets plugged into the f function, so that's just the square root of x. Next, square root of x is getting plugged into the next function out, the h function, so that's just going to be square root of x over 3. And finally, this stuff gets plugged into that last function, the g function. That's going to be 6 times all this stuff minus 3. We can simplify that a little bit. 6 divided by 3 down here gives us 2, so 2 root x minus 3. And just for kicks and giggles, let's plug 9 into this and see what happens. So 2 times the square root of 9, that's 2 times 3, which is 6, minus 3 gives us 3, just like over here. So this will do everything you were doing over here in one shot. So, hope you enjoyed our lesson on operations on functions and composition of functions. Until next time, this is Mr. Sutton signing off.